All right, question 11. This is the last example in sections 9.1 and 9.2. And it says to compute the limit as n approaches infinity of n to the nth power divided by n factorial, or show that it doesn't exist. All right, so now one thing to notice first is that as n gets large, n raised to the nth power, that's going to go to infinity, and n factorial will go to infinity. And so, like we've seen in some previous examples, it's a question of who is going to win out, who approaches infinity at a faster rate, n to the nth power or n factorial. Okay, so one thing we could do just to get a feel for what's going on is just plug in some values. Okay, so if n is 1, then this expression is just equal to 1. And now notice as I let n increase, when n is 36, we're already at 2.85 blah 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 times 10 to the 14th. Appears that the numerator is winning out, right? If I go to n is 83, oh yeah, look at that, times 10 to the 34th. So it appears that this thing is going to grow without bound. Now, of course, this is not a proof. We need to actually come up with an argument to say why this thing actually approaches infinity. And that's what we're going to do here. Now, this is pretty similar to an example we've already seen, question 6, part F. There we had 4 raised to the nth power divided by n factorial. And this argument that we're going to use for this problem is really similar to that. So you might want to go back and revisit that argument. Okay, so the idea is, let's write this out in expanded form. So I have n to the nth power, well that's just n times itself, n times n factorial, that's 1 times 2 times 3 all the way up until we get to n. And now here's the idea. Okay, I'm going to group the following terms, n over n minus 1, all the way down until we get to n over 3, and then n over 2. And I'm going to leave this n over 1 off on its own. Okay, so now what can I say about each one of these ratios that's been circled? Well, n over n itself is just equal to 1, and for emphasis I just wrote greater than or equal to 1. N divided by n minus 1, well, that's a number that's going to be more than 1. Okay, so like for example, if n was 8, this would be 8/7, right? That's a number that's larger than 1. And likewise, each one of these ratios that follows, right? N over n minus 2, all the way until we get down to n over 3 and n over 2, all of these ratios are going to be larger than 1. So what can we conclude from that? Well, our expression n to the nth power divided by n factorial will then be greater than or equal to this n over 1, which again I've saved on its own, times this thing, n over 2, which is a number more than 1. So notice if I replace n over 2 with 1, and n over 3 with 1, and so on and so forth, that's going to make the resulting quantity smaller. That's why our quantity is greater than or equal to this thing you see on the right. Okay, so now what does this thing on the right simplify to? Well, it simplifies just to n, and we're letting n approach infinity, and so from there we conclude the following, right? Our quantity, n to the nth power divided by n factorial, is greater than or equal to something that's blowing up, right? It's greater than or equal to n, and n is approaching infinity. And so if we're greater than something blowing up, then we must also blow up, right? So the conclusion here is that n to the nth power divided by n factorial, that approaches infinity as we let n approach infinity. Okay, so our conclusion here is that the limit does not exist, and that does agree with what we were seeing here by just playing around and plugging in some numbers. Okay, so that's going to do it for this problem, and I will see you in section 9.3 next, where we're going to start talking about series. All right.